In the last part of my lecture, I would like to introduce some of the findings that we report in the paper from last year, Analyzing Analytical Methods, the Case of Phonology in Neural Models of Spoken Language. And so that was co-authored with Bertrand de Guy and Tafra Ali Shahi. So this paper is about the issue of analysis of neural representations applied to this particular class of models that we are talking about today. But in general, analysis of neural representations has been a very active research area in NLP in general in the last 3 years or even more. Many different analysis methods have been introduced, used, and evaluated. However, until recently, there have been a few systematic studies, and especially few systematic studies within our specific type of model that we are discussing today, visually grounded models of spoken language. And so this is going to be our case study. It's going to be about encoding of phonemes, and so there's been some previous work in the last few years on this. For example, a couple of papers looking at neuron selectivity. So that refers to a particular unit or neuron being activated when a particular phoneme or some other unit of interest is being processed. Then there's been a few papers, some of them, a few of them mentioned here, which have used diagnostic classifiers to decode phonemes. So this is the scenario that we saw a little bit before, where we train a classifier to label fragments or segments of spoken inputs with phoneme labels. And so these papers, as already mentioned, they have some limitations. For example, one limitation that we saw was that the use of a baseline in the form of a randomly initialized but untrained model was typically omitted. Another limitation is the use of only local activations. So by local activations, I mean this will become clear later in this lecture. But roughly what I mean by this is that these are activations which are extracted from only a very short local segment of an utterance, whereas these visually, especially the visually grounded models, often have also representations, learned representations which are more global in nature. They pool over the whole duration of the utterance at some point, and this has not been really studied. So in this, our main contributions in this study were that we looked at two different analytical methods. So the first one is the diagnostic classifier, which is already familiar to you. The second one is the representational similarity analysis, which is a technique borrowed from neuroscience. I will explain it in a bit more detail later. We compare with randomly initialized target models, which addresses the issue of the missing baselines in previous work, and we study the effect of representation scope and pooling, which addresses the second limitations which I mentioned related to the use of local activations only. And so, which models and architectures and tasks do we consider? So we're looking at two different architectures. The first one are gated recurrent networks, a type of RNN, which have local connectivity only, in the sense that the state of the current state of the hidden layer depends on the state of the hidden layer in the previous time step, but there is no like long range connectivity. The other architecture is a transformer, which is based on self-attention, and that has global connectivity in the sense that all the time steps somehow depend on each other. And we're considering two different tasks. The first one is automatic speech recognition, and the second one is our task of interest today, visually grounded speech models. So, yeah, ASR is just a transcription task where the output is a sequence of symbols. VGS is relating the two modalities, the spoken and the visual modality. So to summarize, our target models can be displayed in this matrix. We have three of the four possibilities. The fourth one we did not study because it hadn't been implemented or attested in previous studies at the time when we were doing this work. So we have ASR implemented via an RNN and a transformer architecture, and VGS only via the RNN architecture. Let me come back to the issue of scope that I already mentioned. So either we can have local scope or we can have global scope. And so just to illustrate it a bit more explicitly, this is a schematic on the left, schematic representations of what I mean by local scope. So in here we have an utterance, which is being processed by this neural network, schematically depicted by these three layers. And we are considering only a short segment, a few frames of this utterance. We are trying to locate in the different layers the activations which correspond to that, which is not always completely trivial due to the fact that these different layers may subsample the signal or already pull it in some way depending on how these layers are implemented. And finally, we have a label for that segment of the spoken utterance, and that is typically something like a single phoneme. For the case of the global scope, it's different. We have the full utterance. For each layer, we extract the activations for the whole utterance and then pull them in some way, which is depicted with these gray triangles. And our label is also a global label, which is related to the whole utterance. And so in this case, it's the sequence of phonemes: a bird walks on a beam. And so these two different approaches to represent to what is represented in the network will be considered. So in the case of the global scope, we have to do some kind of pooling, and we consider two different ways of pooling. One is very simple, which is just averaging the activations over time, so we call that mean pooling. Another one is attention pooling, so it's a very simple self-attention mechanism, which is equivalent to learned weighted average over time. So instead of like having the weights the same for each time step, they are actually learned. And so how can you relate these activations, they're either the global or the local activations, to the phonemes or the phoneme sequences? You're already familiar with the diagnostic classifier. That is typically some simple model, maybe a linear model or one or two layer MLP. And this in our experiments we use a linear model. And then the activation vectors are features, whether they are pooled or not, depending on the scope. And so the second way of relating activations to phonemes is via representational similarity analysis. And so this is a technique which was introduced first in the neuroscience community, but is now also commonly used for analyzing neural networks. And so for this, what we need are similarity measurements between pairs of activation patterns. For example, we can use the cosine similarity for that. We also need a set of measurements between pairs of phonemes or phoneme sequences. So for phoneme sequences, we can use something like a Levenshtein distance. So what we're doing here is, for a number of utterances, we represent them in two different spaces, so to speak. So one space is going to be the space of neural activations according to some particular layer. And within that space, we measure how these utterances are similar to each other, and we can collect all these different similarities in a matrix. So this is the matrix which denotes the similarity, the patterns of similarities between different utterances according to the neural activations. And then we use a second representational space, and in there we denote each utterance via its phoneme sequence corresponding to it, and then again we measure all the similarities between these utterances using something like Levenshtein distance, and again we can collect all these distances or similarities in the matrix. And given these two matrices and these two representation spaces, we can then simply see how correlated these similarities are. So we never directly map one representation to the other. Instead, we simply look at the similarity patterns in one space and the other, and then how they are correlated with each other. And so we have these two different types of relating activations to labels, diagnostic classifier and RSA, and we have two different scopes, and that gives us the four different analytical methods. So local diagnostic classifier, local RSA, global diagnostic classifier, and global RSA. So let me start with local diagnostic classifier. That is perhaps the most obvious case. In here, we simply train a classifier to map an activation vector to an atomic phoneme label. For local RSA, we use the cosine similarity between activations, and then binary similarities between phonemes corresponding to these local activations. So either the phoneme is the same or not. So we don't have like a graded similarity, but just binary similarity in this particular case. For global diagnostic classifiers, we have binary vectors encoding presence of phonemes as targets. So we have we are using here the global scope, so the whole utterance. So our target vector that we are using as the target, as the output of our classifier, is simply a binary vector encoding which phonemes are present in the utterance. And pooled activations are going to be our features here, so the activations pooled over time. And finally, for global RSA, we will use something like cosine similarity between pooled activations on the one hand for the one representational space, and Levenshtein distance between phoneme strings for the other representational space.